A little example here of using multiple integrals. In this case, it would be a triple integral in order to find mass. We are integrating a density function in order to find the mass. The density is given. This structure, whatever it is, gets more dense as you move up along the z-axis. The density is equal to the height on the z-axis. We're also given the surfaces that define the structure, the plane z equals 16 and the paraboloid z equals x squared plus y squared. And that paraboloid is just an upward opening bowl that looks like this, and it'll go up to z equals 16, and as I mentioned, the density is increasing as you go up. So this is our surface, this is our structure, it's the area inside that bowl, and we want to find the density of it. So density is found as a triple integral over the total mass is found as the integral of the density. So we want to integrate the density and get the total mass. So that's our mass right there. And in this case, as with any triple integral from this point on, we've learned how to do triple integrals in rectangular, spherical, and cylindrical coordinates. So with any triple integral we do, we have to stop and think, should this be done in rectangular, cylindrical, or spherical coordinates? There's nothing spherical about this. This structure is not a sphere. It's not part of a sphere. The thing we're integrating, the density, doesn't have an x squared plus z squared plus y squared in it, so that's not spherical. So let's eliminate spherical. Rectangular, this would probably be pretty tricky because of the circular nature of things. If we look at the shadow of this bowl down on the xy plane, that's going to be a circle down there in the xy plane. So the double integral, after we integrate in z, the double integral is going to involve a circle. This is probably something we want to do in cylindrical coordinates. Remember, cylindrical coordinates are polar coordinates in x and y with the z thrown in. So a circle down here in x and y down there would lend itself well to polar coordinates, and anything that would look good in polar coordinates for a double is going to be good for cylindrical coordinates in a triple integral. So we'll use cylindrical coordinates. In cylindrical coordinates, we want to go from 0 to 2 pi in theta. We're going all the way around that circle down there. We actually need to know the equation of that circle in order to proceed, and we can find it. The equation of the circle, this circle here, it's the same circle, is found by looking at the intersection. Z equals x squared plus y squared with z equals 16. Right, those are the two surfaces. We have the paraboloid and we have the plane, z equals 16. So if we set those equal to each other, x squared plus y squared equals 16 gives us the intersection. The intersection is just the circle of radius 4 centered at the origin. So radius goes from 0 to 4. And finally, the z coordinate, we have z in this structure. If we're thinking of what z is doing, z goes from the bowl up to the surface, up to the plane, z equals 16. So z is going from that bowl, which is x squared plus y squared. But in polar coordinates, that's r squared, or cylindrical coordinates, that's r squared up to 16. And then we're integrating z, dz, dr, d theta. I'm going to leave it here and let you do the integral. The integral here is just power rule throughout, each power rule in z, and then later power rule in r, and then just constants in theta. So the integral is doable. I want to talk about the setup. That integral represents the total mass of this structure because what we're integrating is a density.